So hello EPC! Yes, energy! Awesome. So welcome to my speedrun for about 200 slides. I hope you enjoy it. I hope it will be on time. We're not running out. I will do my best. So my talk is LEGO Horizon Adventures, procedural optimizations, going from PlayStation to Switch, talking about how we approach it in a more procedural way to make a nice pipeline that worked out. So first, in case you're not familiar with the game, I'm going to quickly show you the trailer so everyone knows roughly what this is about.
I got you right where I want you.
I see. In the far future, there are no TVs, just beautiful and totally not boring nature everywhere. Oh, and giant robotic dinosaurs, of course. But you're not here to listen to me. This is a game, not an audiobook.
Oh, this is gonna be good.
Oh, bricks are gonna fly! Now, time for paddling! This is gonna turn power hands.
Oh my god!
Right.
How do you like this? You sure it's dead?
Wow, look at that!
That's your stuff. Let's do it.
Gosh, got fabulous taste!
Oh, stop. Yeah, I know, but that's it. That's it.
Always leave a place better than you found it.
Hello?
Yep.
Drop that pizza!
Go, stop.
I need to like them.
Let's join Eloy as she embarks on an epic adventure.
So that was a little bit about the game itself, in case you have not seen it. Then this other part, you might be wondering who's in front up here. So what about this guy? So my name is Simon Verstraete. I'm a senior tech artist at Studio Gobo. I worked on this game. Previously, I also worked at SideFX Houdini. I did some tutorials. I also made a few lab tools. So yeah, maybe you've seen one of my tutorials. Who knows? I've been doing Houdini and proceduralism for a bunch of years. So yeah, I always been liking exploring all that stuff. And here I already got a first little tip for you guys. The first little tip is working on a Lego game is a great way to get more Legos. I mean, if you need a way to get more Legos in your household, or you need to justify buying Legos, I mean, working on together with Lego Group, great way, can recommend it. My Lego collection grew definitely. I had an excuse, it was reference. But now on more serious notes, some of the topics of today that we will go through. So first of all, trying to give you some goal and context on what's going on and what was needed. Then we're going to go through a brick pipeline and then the mesh pipeline for that. So let's go. So goal and context to give you a bit more information. In a more abstract way, the game is fully built with Legos, as you saw from the trailer. Every single thing in the game is supposed to be Lego, or at least feel like Lego. So it's a Lego game fully built out of Lego bricks. It's a more top-down game, so we can sometimes leverage that in optimization, just useful. And we're also using Unreal Engine 5, which helps us in different areas, but also, for example, making a multi-platform release. On day one, we released on PlayStation, Switch, and PC. Looking at the game, how it looks on PlayStation, so you can see it looks quite nice, high fidelity. We benefit from Nanite, Lumen, all the latest and greatest that Unreal offers. So we really have like a really nice image. And again, everything is built with Lego bricks. You can see it here. Also the main menu, you can really see it's everything built with Lego. It looks good. And of course, playing it on PlayStation, on PC is of course the best version. I was of course talking about another version as well, which is the Switch. So let's take a look at that. Oh. Did something went wrong? Oh, this is definitely a developer screenshot. The game looks more like this. So we have something that looks very, very close, and I have some more comparisons in a moment. So we try to stay as close as we can to the original look, feel, and shapes of what we have on PlayStation to represent roughly everything on the Switch as well. And I think we did a nice job on getting that feel of Lego from a PlayStation to the Switch as well. So everything still has this nice colorful feeling. The shapes are still kind of feeling like Lego and so on. Also even Digital Foundry, which is a YouTube channel that often talks about game technologies. They quickly mentioned that this was sort of like a masterclass in bringing a game to multiple platforms, just because scaling from PlayStation to Switch is a big difference, and we were able to do that, and also performance-wise, the games run really well. In case you're not really familiar with working on different platforms, I brought up some teraflop numbers. So PlayStation 5 has around 10, a PC can go from 5 to 20, and a Switch has 0.5 teraflop powers. Most important thing on the slide is at the bottom, these stats are from Google. I don't know how accurate this is. And on the other hand, but Simon, teraflops don't matter, and that's kind of true. Like as game developers, we're not really using teraflops as accurate way of describing a performance of our game. So the reason why I'm bringing this up is try to understand that the PlayStation and the Switch is a huge difference of hardware, as probably most of you know, but also from the editor perspective as well. Unreal 5 can make a build for the Switch, but of course that doesn't mean that everything is supported. Such Nanite and Lumen are of course on PlayStation and PC, but on Switch, however, we still need to rely on your good old classic techniques such as LODs. There is no Lumen, so we have to rely on real-time lighting or baked lighting. So we have to make sure that all these requirements are met to have a scalable game from the PlayStation to the Switch. So in short, each asset that we have in the game, we need to make sure that it works on PlayStation, but that it also works on Switch. That goes in terms of LODs, nanites, geometries, but also goes in terms of like lots of rendering technologies, your materials, the shaders, the post-processing, all kinds of custom technology that we built need to work on both of the platforms. And also don't question my choice of assets in this presentation. I did not make this asset. Okay, here is more a direct comparison. This is what the game would look like on the more high fidelity platforms, so on PlayStation. This is how it looks on Switch. So you can see, yeah, it kind of look close to each other. You can definitely see the first thing that I would say is very noticeable is that atmospheric fog that is sort of missing on the Switch, which definitely gives the scene a different feel. Because on the Switch, we just had to scale back down on a bunch of things, as you can imagine. So going back and forth quickly, you can see just from a player's perspective view, it kind of looks pretty close. If you zoom in on lots of elements and geometries and things like that, you will see that, of course, we have a way lower topology and so on and so on. But in generally, the game looks pretty close and also just feels quite close. You can also look at the shadows, which is also pretty clear here that we use cheaper meshes to reduce the shadow depth cost and so on and so on. So that's a little bit about that. But now let's go into one of our pipelines. And the first pipeline to discuss is the brick pipeline, because it's a game built out of bricks. So as soon as we can improve bricks, we can improve the overall quality of the game. If you're not familiar with Lego bricks, they have made over thousands and thousands of bricks. I don't even know the official number. It's very high. Like there are thousands and thousands of unique individual bricks. And for us as well, like what do we actually support? We cannot just simply support every single brick out there. So we have a pipeline to manage some of this. And it basically simply starts by making a list on what we want. And this could be simply done, for example, in Excel. So we just list down all the bricks that we want. This could be added and removed over time. That's the reason why we built a timeline. But we basically at some point decided that, okay, let's start with, let's say 1,000 bricks. Let's see how far we can get with that. And then from there, we have our starting points. Then we go into some processing. So we use a bunch of different software and packages to get this all done. So the processing, so let's say Python takes the list with all the bricks, sends it to Blender, and Blender will do some things with geometry and so on. And then we bounce it around, and then we send it to Houdini, where we do some more automation, also maybe sometimes validation in case there's issues with UVs or geometry. We can always automate that and validate that. And then we're going to spin it around, and then we're going to send it to Substance Painter, where we do our final bakes of these assets. Then our final outputs will be just meshes. So for each brick, we will have FBX files, and we also have some textures that go along that. So that was a quick overview of that, but now some details on that. So one of the reasons why we have this pipeline is that we can control the bricks. We have a list, but we also need to make sure that it lives up to the quality that the other people, the art directors and art leads want to have in the game. So first point could be controlling topology. We want to make sure that we have a nice topology and also consistent topology. So for example, that everything is nice and round, or if we want to reduce these meshes, that if the topology is cleaner, sometimes it's easier to work with rather than some random stuff. So controlling topology is important. also is here we already start thinking about optimizations. For example, for each brick that we have, we will create a high version and a low version. The high version basically is what we use on PlayStation or what we use with Nanite. So we can actually afford the additional bevels, extrusions, the additional geometry we can actually render through Nanite now. But on Switch, however, we need to make sure that we have something that is really, really low. So as you can see here, we're just going to have a low tube and we're going to rely on baking out textures to get back all the details in those bricks to still have that visual detail back in there. Once we have roughly figured out some geometries, we're going to go into some unwrapping, where we just need some form of UVs that roughly work for those bricks and projects. Each brick also has a very specific name, like 3003 or whatever. Like each brick has very specific names. So we're going to have to make sure that that's consistent throughout the project as well. And there's a bunch more data that we can have, and everything else, metadata related to the bricks, is also saved. So either saved on the mesh or saved on an additional file that we can always have. So for example, think about stud locations, or where all the connections are, or where all the stickers are, or the decorations. So all interesting information around bricks that we can use will be saved, and for later usage for other pipelines, we can just always reference this data and then do something with it. Now, I do mention that, yeah, we do a bunch of procedural stuff and this is all automated, but in the reality, we did not figure out the magical solution for topology or unwrapping. So we did not figure it out. And in some cases, an artist can model a brick in 10 minutes, while I would struggle the whole day figuring out how to generate one specific brick perfectly. So in my opinion, it was just not needed that even a procedural system doesn't necessarily need to be perfect every time. We had a pipeline where there was manual authorization possible, because on the Switch, for example, on the Switch, every polycount really matters. So we need to make sure an artist sometimes can optimize it better than just simply poly reduce it. So we had to make sure that everything made sense and is good enough throughout the project. Now, so hey Simon, but now also what about unwrapping 1,000 bricks? So that's some of the geometry stuff, but what now about unwrapping them? And the obvious answer is we don't want to have a texture per brick, because then we have thousands of textures in our game. We're going to basically merge textures, as you guessed it. So we're going to create something which is called the texture atlas, which is basically grouping the bricks in different baskets. So as you can see from this image, this is quite visual. So we're going to create these groups of baskets, and each basket has like a bunch of bricks. So in our case, let's say we have 1,000 bricks and we have 10 textures. That means that each texture holds 100 bricks, and then we just bake it into a normal map and so on. Now we went a little bit further. We added a little bit of additional stuff on top of this. We designed, or I came up with the idea to, like, what if we have like a slotting system? What if each brick, here is each random color represents a brick, owns part of the texture. So for example, this brick, which is 3003, owns the UV space in that area specifically. So that way we're not just out UVing everything together. We're basically just saying that based on the briquette size and complexity, we're going to find, or we're going to calculate different areas where the UV should be stored. So that way we actually have lots of control and understand where we can place these assets. So if something breaks along the line, which could be possible, only that brick will break, and we're not destroying the whole texture, because one little geometry issue or UV issue could break the whole texture in theory. But this solution or this approach would basically solve that sort of. So we do this 10 times, so that we have in total, to have the whole game, we have actually 10 textures. And based on the assets, or based on the brick size and complexity, we will just divide those slot systems, or try to place each brick carefully so they have somewhat the same texel density and UV spacing. We then export everything into FBX files, bring it over to Substance Painter, which also artists could help on top of that as well if they want to, but it's all, again, automated as well. So we bake out things like your normal map, curvature map, thickness map, and ambient occlusion, and then also for Switch, an opacity map, because again, we want to keep the geometry as low as possible. So sometimes you just have a simple mask. For example, for foliage, we'd rather have like simple planes, or something super simple, and then just carve out the detail with a mask shader. Now, talking a little bit about this approach, some pros and cons in this, because definitely has some pros and definitely has some cons. Like I kind of mentioned, that each brick has a specific part of the texture. That means that we can only update specific parts. So let's say a certain brick is broken, or an artist made an update on a few bricks. then we can only specifically focus on regenerating those parts, and we understand perfectly where the geometry is, where the UV is, and so on and so on. So we can focus all the effort. So it's quite predictable and deterministic in that way. So we are not taking any big risks of breaking UV data if that would be an issue. And again, we have 10 normal maps to cover most games or all the bricks in the game that we have, which is really nice. Definitely here are some quick cons on doing this approach, is that we cannot magically add more bricks because again, if we decide roughly on 1,000 bricks, we cannot add another 1,000 to it, because then we just would increase more textures. That would be sort of the solution, unless you have like space that you have for this. Then also about what if we start to remove bricks? What if suddenly at some point the artist came to us and been like, oh yeah, these 200 bricks, we're not going to use them anymore. That means that suddenly all my space that I reserved for these bricks will now be gone, and we're just losing texture space, which is not necessarily beneficial. So we have to regenerate the whole thing then in theory. Texture density wise, because we're doing this approach, yes, we're losing definitely some texture density. But to be honest, in our game, we're baking at 4K resolutions. It's not really not that noticeable from this top-down view that we have lower texture density. Only if you maybe zoom in, or maybe on some cinematics you could discuss it. We don't have texture density to actually have like baked down small normal text or details in the normal map and so on. But for us, it was just more than good enough to just have something that works. Now, a quick overview of this pipeline. So again, we start out with a list of bricks. This could simply be in Excel, where we just list everything that we want. Then with Python, we're going to start some processing. We're going to start actually two. So like I mentioned, we're going to create bricks for Nanite, so the high brick. We can also then make a brick for the switch, which will be the low brick. We're making a combination of Blender and Houdini. Blender is mainly used for manual authorization, so we have some plugins as well that tie into this pipeline. So if an artist wants to overwrite the geometry, they can do that and then press some buttons to put it back into the pipeline. Houdini again is just mainly for automating. If we need just a simple proxy for a placeholder, then we can just generate it. We also then have the whole Atlas and wrapping system that I talked about is done in Houdini. Then we bake everything in Substance, and then in the end we export into FBX files, textures, and metadata if needed. That could be useful for later on. So that's roughly a bit about how the bricks were processed during that project. Now, since we have all the bricks, we now can go into actually making meshes. So we have now actually something to work with. The mesh pipeline, I like to just say it is just like describing how you build Legos. It's like an instruction sheet, right? We have the bricks. The only thing we need to do them is assemble them in the right location. What is important for this pipeline is that it needs to be artist friendly. We want to make sure it's in Unreal, and artists don't need to worry about optimization. So let's take a look at an artist's perspective before we jump into some details, because it's interesting to see how an artist will work with this, or how ideally an artist should work with this. So what is quite unique in our game is that we're not using any classical, or we're not often use very classical 3D packages. We're not using Max, Maya, Blender. They are using this Lego software. Here is a little video of that. This is me trying to build something. I'm not really good at this software. But you can see this software is just placing brick by brick. So that's how most artists in this project made the assets. So all the assets were actually roughly made using this software brick by brick. So yeah, they were actually literally playing with Lego bricks during the development of the game. So after a while, they actually make something good. So on the right side, I have an image of an asset that actually looks good, rather than me trying to build something. So once they figured it out, they made some cool assets. They go into Unreal. And in Unreal, yeah, this is the most default screenshot of Unreal that I could find. But this will be enough for my point. They can basically drag and drop that Lego file from the Lego software. And we had a plugin to just import these files. And instead of saying importing FBX, it says like importing Lego mesh or Lego model or whatever. And that's sort of how an artist would then get their models in the game. So for them, it's almost the same process as like importing an FBX file. You just make something, drag it in the game, and then they have it. Now, the only thing that they are missing is they never have any context about optimization, because that Lego tool doesn't give you access to polygons or vertices. Like, it's just basically you make the asset, but the artist at this point never really understands how much polygons they are spending. And that's basically what our job, or what I was trying to do, which I will talk about more in a moment. This menu as well, we also have a rebuild option in this menu, which is a re-import, rebuild. And once someone would press this, there are a few reasons to do this. For example, if they would make a change on the visuals in that Lego software, they would just press this button and it would just get the latest in the editor. But also we do all the optimizations as on here as well. So all the LODs are calculated once someone triggers this rebuild. So if in case I would improve my LOD logic, we just need to rebuild and then I would see the latest LOD changes. And again, anything related to brick data might also require this rebuild in case, again, a brick would break. It's possible that a brick could break. Then we might need to rebuild to just refresh all the data to make it nice. And we can also do this overnight. So don't think that we're asking people to manually press this button all the time. So let's say all the trees are broken in the game. We're just going to basically overnight select all the trees, put it on the server, and the next day we can come back with everything refreshed and as expected to be. So that's some nice automation to make sure it's all up to date. So this sounds exciting, but let's now take a look at some more detail on how that process goes. So let's break it down into a couple of steps on how we get there. So of course, I'm going to start here in Unreal. Unreal also has always reference to that Lego source file. So in my opinion, Unreal is sort of like the manager of this Lego data. So Unreal keeps track of the Lego data. But to get our data or Lego model into another package, we're going to make a simple JSON. And again, the JSON is basically describing how the model should be built. And if you're not familiar with JSON, here's a very rough example. This is definitely not what we've used, but you might just get the point. So we're basically making like a list of all the Lego bricks that are needed to make this. So we have the position, the brick name, the color, and so on and so on. So we just have a very simple standard format, and Unreal makes this so we understand that Unreal sort of always has this output of the same structure. So we have that some consistency there. And then we open this in Houdini. So Houdini imports the JSON and then makes the mesh, optimizes it, and sends back an FBX file. And this FBX file just gets imported as a static mesh. And that way we have sort of like have our pipeline a little bit there. So when an artist would press a button, or if someone would import an asset, this is what's going on in the background. And it's of course all hidden from the user's perspective. They would just see like loading or waiting. And this only takes a few seconds to then calculate. Now let's take a closer look at some of the Houdini approaches that we've used to optimize the geometry. So like I mentioned, first of all, we need to import the JSON. So we have that JSON file that basically lists every brick that is required. So in Houdini, we just read the JSON with a Python sub, and then we're just going to create a point cloud, and we're going to assign all the attributes that are needed. Like we have the position, we have the rotation, we have the brick color, we have the brick names. So we have everything that's needed. So again, these points just hold a reference to a brick, so we can reconstruct them later on. So we don't want to construct them yet, because we're going to have, for example, our PlayStation processing first, or in other words, the Nanite one. In here, we're going to create a mesh especially for PlayStation or for the Nanite version of the game. So we're going to load our high fidelity brick. So remembering from the brick pipeline how we made a high and a low version, we're going to load the high version, which has the most details into it, and we're going to make our geometry from that. We're also going to apply internal removal of faces, because often when you place Lego bricks on top of each other, there is a bunch of overlapping and internal faces that we can delete. In theory, you could say, like, yeah, Nanite could handle all of this additional geometry, but I somewhere still did it anyway, and I believe, like, in terms of file size, it will be lower. Maybe some overdraw will be better. It also has to load a little bit less in memory. And here is an example of some of that. So this asset, which is a bigger asset, by default has around 400,000 triangles, but with some optimization, we actually can delete half of it. So half of the triangles could be gone, because they're just never seen. Like visually, there is no difference between the 400,000 and the 200,000 triangles. It's just purely internally deleting the geometries. Well, one of the reasons why we actually have this high number in polycount is because we are including all the studs on the Nanite mesh or on the static mesh itself. So because Nanite actually just handles this really well. And at some point, we even experimented with having the actual Lego font on these as geometry, which is definitely overkill. You should not do this. It's possible, but it's easier to just have a texture and then tweak the texture and then just call it done, rather than having to update all your geometry in your game. But we tested it, but it's not. I would say it's not recommended doing it, but it works. So once we figured out roughly how to make a PlayStation mesh, we can go and also try to make a Switch mesh. And again, remembering from the brick pipeline, we make a low version. So we're going to load the low polygon version from the brick pipeline, and we're going to also apply removal of inside faces. We sometimes need to do additional poly reductions because we do want to control, in case it would be a bigger asset, we do want to control that poly count a lot because the Switch is not able to handle a large amount of polygons. We don't include the studs on this mesh because the studs on the Switch are instanced, because that way we have in Unreal more control over the stud locations and the instancing and how far we want to render the studs and so on. So we have lots more control over that. Here is an example of some of that reduction. So by default, this asset would be 5.5K triangles, which is not that much. But after some optimization, we have 30% reduction to 3.9K triangles, which is pretty nice. So scaling this to the whole game means that we can have 30% less triangles to render, which is pretty good. Now, next thing is, I do talk a lot about deleting internal faces, and there are many approaches for this, but I tried different approaches, and what kind of worked most of the time, or for most assets, is the following idea, is that what if we just try to mimic the camera around an object? Because essentially we have a top-down game. So what if we only just try to fake the camera around your object? And that's why I have this sort of rough example where I have like this half sphere casting rays to that asset. So that's one way that most of the time actually did pretty good results. So we're going to shoot a couple million of ray casts from those angles to the asset. And from there, we have a good idea of if a primitive received a ray cast, means it should be rendered. It means we should not delete those primitives. And that actually worked pretty well. Now, it does have some downsizes, and that's why I introduced an additional validation pass. So we're not going to simply stop by doing a few raycasts and calling it done. We're going to do a validation pass because in some cases, harder areas or smaller triangles might sometimes be missed by raycasts. We're only doing a certain amount of raycasts. We're not going to do an insane amount. We're going to do a couple million, but we're not going to do more and more and more. So at some point, I was just thinking about what I can do as a validation pass, and I would do a sort of like a neighbor check, and this actually kind of worked pretty well. So what if each valid primitive could check their neighbors, which is not valid, and from there, maybe do a reverse raycast or try to do some checking on those to see if they should be kept or deleted. So from there, trying to get a bit more context on each non-selected primitive there. And that actually kind of worked pretty well to remove most of the gaps in the game. So most of the assets actually were pretty fine with this approach. After that, we have to store some data on the assets as well. So we roughly figured out how some of the geometry would look and would go. And we go to data storage, which is basically UV and vertex. On the UV, we store our base UV from the atlas. We also need to store a reference to which one of the 10 textures to use. We also store the color data in the UV channel and also recoloring data, which was a custom technology which allowed us to recolor any brick at any given point. If an artist wanted to change the grass to another color, they could just simply paint it without having to go back to another packages. They just had a brush tool in Unreal to change that. That's one of the most common data that we stored. Of course, there are exceptions where we did store more data in UVs if needed, but this is sort of like the most common data. Also for the vertex, we have just the ambient occlusion of the asset itself. We have then also a random grayscale per brick, and also a bunch of masks in case in the shader we want to do slightly different roughnesses on different special bricks. So an artist could give me a list of bricks and be like, hey, I need to mask out these specific bricks because in real life they have like slightly different roughnesses. Even though I might not see it, they apparently see it, these slight differences in roughness. So yeah, these are all some interesting information that sometimes based on the assets might slightly adjust, but that's kind of our base information that we want to have on each asset. Now from here, we're kind of done with PlayStation. So on PlayStation or on Nanite, we just need to make one nice solid mesh, and then we can just basically give it to Nanite. And from there, we actually had no issues, and it was handling that really well. Now on Switch, however, we have one nice good model that is relatively low in poly count, but of course, we still need to have our LOD chain because we rely on LODs for our optimization there. And this is how an LOD chain could look like on the Switch. So on LED 0, we will basically say that this is only used on platform for PlayStation. And LED 1, 2, 3, 4, 5 and beyond will basically be a Switch exclusive chain. So LED 1 and 2 are basically the most important LEDs in my opinion, because this is what the player will most of the time see. So we try to keep as much of the data, the break data, intact. And the way that we do that is by simply just saying that we rely on poly reducing, a more aggressive form of that raycasting removal thingy, and also trying to see if we can merge and fuse elements together. But it is very important that in terms of topology that they're kind of like close, because a lot of the data is stored in the UVs and in the vertex, so they have to be kind of close to each other so we can still benefit from the texturing that we have and so on. So they still look kind of close, but still a little bit cheaper. And then anything beyond that, like LED 3, 4, 5, and so on, we don't really care about the original geometry anymore, and we're just going to go for a more remeshing approach. And yeah, so we do remeshing, voxelizing, whatever you want to call it. We're going to just basically make a new mesh and then poly reduce it. We have a very specific attribute, reducing, and we can also delete some internal faces if we want to. Now, I do want to say LED 4, 5 are very far away. We have a top-down game, and most of the time we don't really see this. We do often generate this as backup, because in some cinematics, they went quite crazy and suddenly changed the cameras in all types of directions. So we do generate this, but also for shadow casting. So on the Switch, we do use one of these lower models. So LED 4, for example, could actually be a good candidate to be a potential shadow caster. So we have that lower cost in the shadows. So we just have that in case it's needed, but it also could be tweaked. Like we can say that we only want 3 LEDs as well. So we have also options to override it if needed. And also here, we don't necessarily going to bake things down into textures or imposters or anything like that. We're basically going to save everything in the geometry. For example, the color here is purely saved in the UV. And if I can keep the UV data intact over each LED, that means that all the shaders will automatically work for each LED. So we don't need to worry about making something specific for LEDs. As long as that UV data is intact, we can sort of always recreate those values. So like I mentioned, if an artist would color the grass from green to blue, it will automatically work for each LED without having to do something special in the materials. It's just UV data that it's referencing. So if that is intact, it will automatically work there. Now, of course, this is the most default processing it can do, but in reality, we have different groups or different types of processing. For example, a tree will be processed different from a building. So we have different parts where we make distinctions. For example, we will be more careful with a tree to make sure that it's nicely still have its shape. But this, I would say, is the more default processing. And then this is then roughly the pipeline. So we just export everything as one simple FBX file that has everything included. But we do make one more exception, and that is for transparent or translucency, because Nanite doesn't support that. So we basically decided, why not just export multiple FBX files, and in that way, sort of just have that separated so we can actually still have translucency or transparency material support on the Nanite side. Now, a quick summary of this. So an artist makes this Lego file. They would drag and drop this into Unreal. They will see this importing menu. In the background, we're making a JSON. The JSON gets sent to Houdini. Houdini makes the mesh, exports an FBX file, puts it back into Unreal as a static mesh, and then the artist has their mesh. So that means at the end, each asset has been optimized by default. So an artist wouldn't simply break our Switch build. So they can throw in whatever they want, and we try to take care as much as we can. So by default, we actually have a very steady Switch build every day. Without having to worry about that one asset could break the whole thing. We actually had something that was quite stable along that time. So finally, to just finish up this presentation, I hope you could see that we could save artists time. So by default, again, everything was kind of optimized on the geometry side. Of course, there were many other things I haven't mentioned. There is also a bunch of other pipelines that we also used a bunch of this stuff in. So I mainly talked about static meshes, but we also have like animation and skeletal meshes. So we also do take care of some of that in a procedural way and optimize that. We also have lots of VFX that use procedural approaches, such as the VAT, the pivot painting, and other elements for all the effects. And also things, we also had a foliage placement tool to like scatter around, foliage around the level, so the artist wouldn't have to place every single thing. And we had like all the stud locations, so we can actually snap this scattering tool to specific locations on the stud, so it actually makes sense in terms of Lego and so on. So yeah, there's a bunch more stuff that I didn't have much time to go over to. And you could, in theory, you could say that most assets are actually processed through Houdini in the background. So almost every asset in the game has been gone through some of the things that I've shown you here today. And the last thing that I want to say, Houdini is awesome. I'm very biased, but yeah. Thank you so much. I don't know, is there time for question or did I overrun?
Hi, sorry. Yes, great talk. That was so cool. Have you thought about exposing this tool to players so that they can make their own things and have them in sort of a game down the line?
No, I mean, this is also partially owned by Sony and by Lego, so
I mean, have they thought of anyway?
Yeah, I mean, it's more of a. I would love this to be that it would be more out there and that more games could benefit from this. But yeah, officially, as you know, these files are owned by these big companies, and they will make this decision if this will be public or not. But yeah, I guess that's my official answer. I guess.
Thank you.
Please, no Apex question.
So, Apex.
Yeah.
No, as a fellow Lego digital veteran sufferer guy from the Lego movies from way back, how did you do decals for static meshes?
You mean like the stickers and yeah. So we basically for each brick had a UV channel. So we had an additional UV channel if you wanted to put like some type of sticker on a brick. So it was purely handled. If an artist would make an asset that has stickers on top of them or decoration data, we would generate these additional UV slots, and then in a material, in Unreal, we would make a special material that has these stickers. So we would make an exception there, and that's roughly how we put like the stickers and the decals on top of the. I mean, it's not really decals as you would say decal in Unreal, but it's just purely material with a texture and UVs handling that.
I think that the first question was about the tool to create the Legos, and I believe that one is available.
Oh, the tool that you can actually place bricks by yourself? Oh yeah, that one is for sure. You can just there's a bunch of websites. I mean, I think you can find other people's creations and you can upload that. I think it's called Bricklink, if I'm not. Yeah. Yeah. Don't talk to me, but we had the pain of all the file formats as well. But yes, you can definitely find this Lego software.
I think it also automatically syncs the database of available pieces with every iteration that they introduce new stuff.
Oops, I'm running.
Great talk and really, really well communicated. It was very clear. Were there any particular pleasures or pains that stood out from integrating Blender into that pipeline? And for the UVing, I know, for example, Rhizome UV and UV Packmaster have some really sophisticated algorithms for that. Is that something you looked at?
So those were two questions. So the first one is, I mean, Blender was mainly used through that brick pipeline, and the main thing was making a little add-in that could load an FBX file and save an FBX file in the right locations and then submit that to Perforce. That's roughly the only thing that we had to do. So it was relatively easy to make a simple little add-in with just a few buttons. Like I mentioned, each brick has a certain name. So let's say I go to an artist and I say brick 3003, you need to work on it. They would go in Blender, type in this number, press the button, load brick. They would remodel it, and then they would press another button, export, and it would place it in the right folder locations that we expected from it, and then just submit everything to Perforce. And that way, it's sort of like roughly fitted into our pipeline, where we always just looked at certain folders for what FBX files to look into and process for our pipeline. And then on your second question on the UVing, yeah, we actually really didn't explore much on that front. Even when I look back at this Atlas system, I kind of like, I feel like I could have come up with something better, but I just quickly made this in a few days and people liked it. And I was like, sure, if you like it, we just keep it then, right? It works. So sort of like stick throughout the project. And of course, at a given point, it becomes very risky to regenerate this because every single thing in the game is dependent on this. So you don't want to simply rebake this a month before release or rework this a month before release because every single thing in the game uses this. So yeah, at the end, of course, we basically said like, yeah, it's not really worth it. Figuring out this maybe a little bit more text density in the bricks is not going to change the whole game at that point anymore. But definitely, it's something that I would like to have spent more time in, but just made a simple solution that most people were satisfied with, and I just rolled with that as well. I'm not going to make my life more complex if it don't need to be, right?
All right. Thanks for the talk, Simon. So I was wondering, when you talked about the brick and the mesh pipeline, I understood it as the brick pipeline is for all generic pieces, whereas the mesh pipeline allows them to use any piece from the Lego library because you're baking it all down into a mesh FBX. Is that correct?
So the two pipelines work hand in hand. So first, the brick pipeline makes the bricks that everything in the game uses. So the brick pipeline is really about controlling the quality, making sure the topology, the UVs are good enough. And then once we figured out those bricks are good enough, we use those geometries from the brick pipeline to construct the assets. So the brick pipeline is very important that everything kind of relies to it. So that needs to be good. So they go hand in hand. I mean, the mesh pipeline uses only the bricks in there. So we're very restrictive in terms of what we use. So we don't have every support for every single brick.
Yeah, that makes total sense. So in this case, when they were building the meshes in the Lego Bricklink software, were you able to give them a CSV that limited their palette of or library of assets even when building in that software, or was that something they had to keep track of themselves?
That's a good question. So we kind of sort of tried to hack some of the software because it's not really open source, and I don't know how much I can say about the thing, but we had some little thing that could force it to not show everything anymore. So we were sure that if something was built, but even in the real, we also had validation. We did lots of validation in the real because at some point, I mean, the project started with almost like a free-for-all, like do whatever you want. But of course, after you're going to start serious production, you want to limit them. And we then, of course, implemented validation. Once we figured out, like, these are the amount of bricks that we want to use, we still have assets from the beginning, and then we just have Unreal validation complaining about, hey, this asset still references to old data. Please, someone needs to update this because there will be issues. And someone, of course, over time then updated everything.
Thank you for the talk. I was wondering if you did any randomization on the placement or the rotation of the bricks to replicate improper placement of Lego bricks.
So in the mesh pipeline, we kind of kept it pretty close to what the people built in the Lego software itself. I added a toggle for adding random rotations because I remember artists saying like, hey, what if the floors had like more random rotations so they're not like a perfect straight tile? So I did add that, but in the end, it was only used in a few areas, like mostly on ground tiles, because most of the time, I guess they just were happy with how everything came out. But yeah, it was an option, but for some people, I mean, most artists just drag and drop the file and never really looked at some of the options we provide. They were just like, oh, it's just in the game, it works. But they had many options. We actually had a real nice list of options, but I guess some artists are not always encouraged to go through a list of settings. And that's why by default, we just made sure that the default works. And we can always just say to them like, hey, if you want to modify it, here are some options available to you to actually dial in some little details. But yeah.
Yeah, so I guess my question kind of ties in with what was just said. I was wondering, is there any sort of parametric surface modeling that was done with the Lego bricks, or maybe constructive solid geometry? I assume, or I could imagine that it could have helped with the like faces that were occluded or things like LODs and stuff?
So yeah, I mean, at the beginning, we only had like more high poly bricks, and then I generated more lower poly bricks for the switch, because again, the switch was, of course, something that we had issues with. Like it's a switch; it won't run the Nanite meshes on the switch, right? So in the beginning, I generated a bunch of like low poly versions of bricks, but we still decided that someone still needs to like manually help a little bit with that, because it's going to take me a long time to figure out many different situations, because we have more than 1,000 unique bricks that we support, and they are sometimes so different from each other that it's like very hard to like automatically or do some parametric modeling in there. I just sometimes also just rather quickly make something that works more good enough. So we did not necessarily have like a super fancy brick generator on its own. There was some proceduralism there, but again, the most important thing was the manual override option. In case someone felt like it could be done better, it was there. That was, in my opinion, the most logical way, because sometimes modeling a brick for an artist is like, they can look at this and be like, oh, I can do this in 10 minutes or 5 minutes. And it's like, yeah, that might actually save me time as well, so I can focus on some of the other pipelines.
I'm here. Yeah, thanks for the talk, Simon. So you mentioned that within your pipeline, for low versions, you went with LODs. Have you tried H-loads and imposter solutions in terms of like performance, art style, art consistency, etc.?
I remember talking about the engineers about some approaches and some ideas, but in the end, I kind of just trusted them and just listened to them. And then they also had like, they actually did a lot more performance testing in terms of what's the best. And I kind of just closely worked with them and I listened to their advice. Like I remember my original tool had support for imposters as well. Like we could literally make every asset in the game into an imposter. But one of the engineers was like, yeah, we're going to try to get rid of imposters because it's like a very different way of like handling these LODs as well. So in the end, what you see is what a collaboration was with the engineers, and it kind of worked out for us well enough. And again, trying to mainly crunch down our scenes as much as we can. We roughly have what we could render on the Switch was roughly around 1 million of triangles maybe. So yeah, I was balancing my benchmarks through that and trying to just improve my LODs over time. And I guess just saw the potential about this pipeline that I could actually achieve this goal. If I was not able to achieve this goal, maybe they would look into other solutions as well. But yeah, I just listened to my engineers. That's all I can say in terms of that. I did not test every single part of the performance aspect there.
Awesome. And another tiny question. Were LEGO representatives were okay with your decision on removing stubs from some of models?
What do you mean? Some of the...
Yeah, you mentioned that for low poly versions, you removed at certain like points, the stubs, like pinpoints to connect other elements.
Yeah, that's you could say that's a good question. I remember from the beginning that LEGO was very specific on how we should destroy bricks. They were like, don't just simply break them in two. They should be still piece by piece. Yeah, I guess it's also depending on how they see this. They don't know all these technologies that go behind this, right? They just see it more from how the game is as a whole. But yeah, I mean, sometimes they were more specific about using the very accurate color rather than if a brick looked good, it was good enough for them. So we could leverage some different areas. But yeah, it's almost like this thing where if you would ask them, they might give you a very official answer and like everything needs to be perfect and you should not mess around with this. But if you never ask and they're okay with it, you can sometimes just leave it, right? Because you're going to this endless way of they want everything to be perfect. But in reality, you don't have time to do every single thing almost perfectly. But yeah.
Okay. We are slightly behind schedule, but I'll ask a question anyway because I really feel this.
I saw this in your talk and a few other talks that you discuss a pipeline where it goes from like Houdini to Python or to Blender and back and forth, changes a whole bunch of software, and often somewhere along the middle, FBX shows up. Is that because it's a fantastic format, or is just a Stockholm syndrome?
Yeah, I mean, just FBX is the most basic one to work with. I mean, Unreal just supports it easily. We just import it as a simple static mesh. There could have been other ways to do it, USD or other things, but it's also, when I would bring up USD into the studio, they're like, what's USD? And it's like, okay, let's just stick with FBX then. So yeah, it's just convenient. It's been here for decades and it just kind of works. Yeah, that's all I can say. It just works and everyone just fine with it and everyone is familiar with it.
Okay. I think that kind of answers the question. Thank you.
Yes.
Fish.